Okay, let's talk about ODEs involving Heaviside functions. This first section, here's just an example of solving an ODE that involves a Heaviside function. There's absolutely nothing new here, other than this involves a Heaviside function, but everything's the same. You Laplace transform everything, use the initial conditions, solve for y. Everything is very standard. There's only one thing I want to alert you to. You'll get to something that looks like this, and many of you will write it as e to the minus s over s times s squared plus 4. And you'll correctly think I should try to use Maple to do a partial fraction decomposition. And that's correct. Maple won't return anything useful if you do that. A partial fraction decomposition is for rational functions where you have a polynomial over a polynomial. Okay? A negative exponential is clearly not a polynomial. And so Maple is not going to do anything useful if you try a partial fraction decomposition on this thing. Instead, what you do is you say, well, this is e to the minus s times 1 over s times s squared plus 4. And you do a partial fractions on this part. Okay? And you write it as e to the minus s times 1 over 4s minus 1/4 times s over s squared plus 4. Okay? So you factor out the exponential and then you do the partial fractions on the part on the inside, and that's the useful way to do this. Again, if you try to type in the negative exponential into Maple and then do partial fractions, nothing will happen for you. So just watch out for that. But otherwise, everything's the same. I'm not going to go through it. Just go ahead and read through the example. Make sure you can follow the steps. What I do want to talk about is some modeling using Heaviside functions. Heaviside functions, again, we talked about, they're great for representing discontinuous things. So let's think of a problem here. So we've talked about mass spring damper systems where you can have an external force acting on the object. Let's go ahead and assume or let's think about what would happen if the external force is a discontinuous thing. So for example, imagine you have an object with a mass 1 kilogram, so our m is 1, and we have a spring coefficient k is 9, and you have a damping coefficient of c equals 2. Okay, so you're going to write down an ODE that governs this system. Of course, it'll be at my double prime plus cy prime, so that'll be 2y prime plus 9y equals the impressed force, right? So the external force here is 6t minus cosine t between times 2 and 4, and at all other times there's no external force acting on the object. So what's our external force going to look like? So let's just draw a little plot. Between times 2 and 6 there is some force, so 2, 6. Outside of those times there's no external force, and between times 2 and 6 you have something that looks like, well, 6t minus cosine t, so it'll look about like yay. It'll be this squiggly thing going sort of upwards, and then at all other times there's nothing. So this is a graph of 6t minus cosine t. I just totally made that up, so that graph isn't that close, but it's sort of ballpark. Anyway, now let's go ahead and write down our external forcing function in terms of Heaviside functions, and the reason that we'll do that is because then it's easy to solve the resulting ODE. There are other ways to deal with these discontinuous forcing terms, but Laplace transforms really excel in this area. So let's see. This external force, it's nothing up until time 2. at time 2, we want to turn on the external force 16 minus cosine t. So 16 minus cosine t, Heaviside function shifted by 2. And then at time 6, the external force turns off, and then that's it. So we'll say minus 6t minus cosine t, Heaviside function shifted by 6. And that's it. So that is the model of the ODE. Or that's the ODE. Let me see. I did write down some initial conditions here, so I could write that y at time 0 is 1 meter above equilibrium position, and we took above to be negative, and I gave you an initial velocity that is 2 meters per second down, so that would be a plus 2. So this would be the initial value problem that's going to describe that physical situation. Alright, let's take a look at one more example. We have a salt tank. It initially contains 100 liters of water. You've got 10 kilograms of salt dissolved in that water. You've got brine solution flowing in at 5 liters per second. Now the concentration of salt in that incoming solution before time 5 and after time 10, there's half a kilogram of salt per liter in the incoming solution, and during the 5 to 10, there is 1 kilogram per liter in the incoming solution, and you've got a well-mixed solution flowing out of the tank at 5 liters per second. So this is a salt tank problem. So if A of t is the amount of salt in tank at time t, then dA dt is the rate of salt in minus rate out. The rate out is going to be what it always is, so that is a concentration of salt in the tank, and there's always 100 liters of water in the tank, so that's A over 100 times the rate at which solution's leaving the tank, which is 5. And now the rate of salt flowing in, this is the interesting one for us. It's interesting because the rate of salt flowing in is not constant this time. But between times 0 and 5, salt's flowing in at a rate of 2.5 kilograms per liter, right? So if we were to graph this, here's time 5, here's time 10, up till time 5, you are flowing in at 2.5 liters per second. After time 10, there's salt flowing at 2.5, that's kilograms per second, sorry. Between time 5 and 10, salt's flowing in at 5 kilograms per second. So we can represent this. This is the rate of salt in. We can represent that using Heaviside functions. Now, we worked on this in the last video, or maybe 2 videos ago. Let's just go ahead and write down what this is. This will be 2.5 plus 2.5 Heaviside function shifted by 5 minus 2.5 Heaviside function shifted by 10. Okay, and that's it. So all you did, you had to have a rate of salt flowing in, you had to have a function to describe that, and this time it was discontinuous, so you used Heaviside functions to deal with that. Alright, let's do one more. You have a thermometer that initially reads 70 degrees Fahrenheit, and it's placed in an oven preheated to 350 degrees Fahrenheit. After 5 minutes, the thermometer reads 150 degrees Fahrenheit, and at time t equals 10, the thermometer is instantaneously moved to a room with an ambient temperature of 62 degrees Fahrenheit. Assume that the constant of proportionality in Newton's law of cooling does not change when the thermometer is moved. So let's write down what's Newton's law of cooling say here. If big T is the temperature of the thermometer, that says that d big T d little t is equal to a constant of proportionality times the difference between the ambient temperature and the current temperature. Okay? Now, this constant of proportionality usually isn't given to us. It's usually given to us through some extra information about how quickly the temperature of the thermometer changes. So that's what this is going to give us. I'm not going to go through getting that. because it's really not the point here. The point is, how do we use Heaviside functions to set things up? What I want to talk about is, so look, the ambient temperature, we're used to the ambient temperature being a constant. Let's see what happens if the ambient temperature changes. So as far as our thermometer is concerned, the ambient temperature changes from 350 degrees Fahrenheit. It changes at time 10 down to be 62 degrees Fahrenheit. So it starts out at 350, and at time 10 it changes to be 62 degrees Fahrenheit. We can represent this. This is 350 minus, how much is that? That's 288. Heaviside function shifted by 10. So this is the ambient temperature. So if we write that down in our ODE, d big T d little t will be a constant times 350 minus 288 Heaviside function shifted by 10 minus t, and then that's it. Okay, so you can use Heaviside functions in all kinds of places to represent these discontinuous things happening.